Okay, welcome to the explainer. So, if you've been looking at consumer electronics lately, you've probably noticed this sudden, almost overwhelming explosion of AI terminology, right? It seems like literally overnight, our devices went from having simple specs to just a dizzying array of new acronyms, performance metrics, and honestly, some pretty bold claims. We're talking CPU, GPU, NPU, TOPS, petaflops. It is a lot to take in. Okay, let's dive into this, because we aren't just looking at a passing trend today. No, we're looking at a fundamental rewiring of how personal computing actually works. So in this explainer, we're going to cut right through the noise and map out exactly what is happening under the hood of your next computer. I mean, think back to just a few years ago. Buying a computer used to be a relatively simple two-brand choice, right? You'd look at a spec sheet and you were essentially just choosing between an AMD processor or an Intel processor. They were the undisputed heavyweights of the PC space. But, as this quote makes crystal clear, that era is behind us. Today, the chip industry is vastly larger and, frankly, far more exciting. We're absolutely no longer looking at a duopoly. Instead, we are navigating this wild alphabet soup of completely new architectures that are actively disrupting the status quo and totally changing what a personal computer is capable of. To make sense of this massive shift, here's our roadmap for today. First, we'll chart the changing chip landscape. Second, we'll meet NVIDIA RTX Spark. Third, we go inside the AI superchip. Fourth, we'll map out architectures and operating systems. And finally, we'll look at the future AI computer. This isn't just a list, you guys. Consider this your personal guide through the most significant technological paradigm shift of the decade. All right, let's kick things off with Section 1, the changing chip landscape, and specifically the end of the duopoly. To really understand where we're going, we have to quickly look at the historical timeline, the long-standing dominance of traditional PC chips, and why that specific era is now rapidly evolving. Now, what's really interesting about this comparison is the stark divide between the old era and the new era. Looking at the old era, we've got that x86-64 legacy. For decades, AMD and Intel totally dominated this space. They powered everything from your traditional Windows PCs and laptops to heavy-duty workstations and even massive Linux servers. It was a highly standardized world. But look at the new era. This is defined by underdogs and disruptors. We've got Apple transitioning entirely over to their own ARM-based Apple Silicon. We have mobile chips scaling all the way up to handle desktop-class workloads. And we've got GPU-first architectures from companies like NVIDIA aggressively challenging that old x86 legacy. The playing field hasn't just leveled, it's literally expanded in every possible direction. As this new era takes shape, there's one specific acronym that just keeps popping up everywhere: the NPU. Let's demystify this tech jargon for a second. An NPU, or Neural Processing Unit, is basically an AI accelerator. To really grasp this, let's use a super simple analogy. Think of your CPU as the general manager of a company. You know, it oversees everything, opens your apps, runs the operating system, keeps the business moving. Then, think of your GPU as your highly talented in-house graphic artist. It renders 3D graphics, games, all the visual stuff. The NPU, however, is like a highly specialized AI consultant brought in to do one specific, immensely complex job incredibly fast. It handles artificial intelligence tasks like machine learning and neural networking way more efficiently than the manager or the artist ever could. Which brings us perfectly to Section 2. Meet NVIDIA RTX Spark, the AI superchip. We've looked at the broader chip war, but now we need a concrete example. We're going to transition into looking at NVIDIA's specific hardware vision, which serves as a perfect case study for this entire industry shift. Recently, NVIDIA and Microsoft announced this completely new platform. RTX Spark is described as a superchip specifically designed for Windows PCs, and it is entirely built from the ground up for the age of personal AI agents. NVIDIA has explicitly stated that this platform is targeted toward a really wide demographic. We're talking creators who need a massive processing power, AI developers training models locally, gamers pushing high frame rates, and honestly, anyone looking to invest in the next generation of Windows AI PCs. It is a bold stake in the ground for the future of the desktop ecosystem. And to back up that bold stake, NVIDIA released this number, up to 1 petaflop of AI performance. This is absolutely meant to be a shock and awe moment. And honestly, the sheer scale of this computing power is something to be incredibly enthusiastic about. Just as a reminder, a petaflop represents 1 quadrillion operations per second. 1 quadrillion. To put that into perspective, just a couple of decades ago, you would literally need a massive room-sized supercomputer at a national laboratory to achieve a single petaflop. And now, NVIDIA is claiming they can put that level of localized, dedicated AI computational power directly onto your desk. Insane, right?
So the crucial point is, how exactly are they achieving this kind of performance in a consumer device? Let's move into Section 3, inside the AI superchip, focusing on the RTX Spark architecture, where we'll deconstruct the exact anatomy of this hardware.
Let's walk through this step by step to see how these powerful components actually interlock. Step 1. It all starts with a 20-core NVIDIA Grace CPU to handle all your general computing needs. That's the general manager we talked about earlier. Moving to Step 2, it integrates a cutting-edge Blackwell RTX GPU for intensive graphics and parallel processing. Then, Step 3, it features dedicated Tensor Cores acting as your NPU for localized AI acceleration. And finally, Step 4 is the secret sauce, up to 128 gigabytes of unified memory. This is huge because it means the CPU, GPU, and NPU aren't fighting over data or endlessly copying it back and forth. They all share one massive, high-speed pool of memory. When you combine this hardware with NVIDIA's existing CUDA and RTX software ecosystem, you get a machine that is purpose-built to seamlessly handle absolutely massive creative and generative workloads. Looking at the workload distribution inside a modern AI PC really explains exactly why this specific architecture is so revolutionary. In the past, the CPU section would have taken up the vast majority of the pie, struggling to manage tasks it just wasn't perfectly suited for. But look at this beautifully balanced, collaborative effort. General computing takes about a third, graphics and 3D rendering take a third, and dedicated AI acceleration takes that final third. The traditional bottleneck of the CPU trying to do absolutely everything, that's gone. It's been replaced by a highly specialized team of processors working in perfect harmony. Of course, brilliant hardware is useless without software to command it. Let's zoom out from the hardware specs in Section 4, Architectures and Operating Systems. Because even a 1 petaflop superchip needs an operating system to run, and the OS landscape is shifting just as dramatically as the hardware itself. And this brilliantly illustrates how the major operating systems align with their core underlying architectures. It's like watching a grand puzzle come together. Look at Windows at the top. Traditionally ruled by AMD and Intel on x86, it's now seeing a really growing ARM presence. Move down to macOS, and you see Apple's complete, highly integrated shift to ARM64 with Apple Silicon. Linux remains the ultimate flexible platform, right? Supporting almost everything, including open architectures like RISC-V. And mobile operating systems like Android, iOS, and Huawei's HarmonyOS are almost entirely driven by ARM-based architectures. The lines between desktop computing and mobile architecture are just blurring incredibly fast. To really hammer home how dramatic the shift is, just look at the sheer scale of this ARM world expansion. We aren't just talking about one or two companies experimenting here. We are talking about Apple, Qualcomm, MediaTek, Samsung, Google, Huawei, and now NVIDIA with their Grace CPU. Literally all of them are utilizing ARM-based or ARM-adjacent architectures to chase better power efficiency and tighter hardware integration. This mobile-first technology is aggressively pushing into the traditional PC space. And down at the bottom there, we should briefly note RISC-V, which is rapidly growing as a fully open-source alternative for embedded devices, research, and future custom chips. Make no mistake, the hardware foundation of our digital world is being completely rewritten by these players. Let's move to our final section and see how this builds into something that actually matters to you. Section 5, the future AI computer, beyond the CPU. Let's step away from the technical acronyms, the petaflops, and the architecture charts for a second, and look at what this all means for your day-to-day workflow. Because when we translate all of that silicon into real-world capabilities, the list is honestly staggering. And this directly impacts you as a focused learner and creator. Because of this architectural shift, we're talking about devices that can effortlessly render massive 3D scenes. We are talking about editing 12K raw video natively. We're looking at generating 4K AI video right on your machine, running your own private large language models, and hosting local AI agents that actually learn your specific workflow, all while maintaining the ability to play AAA games at the absolute highest settings. Whether your focus is high-end design, complex coding, or just sheer entertainment, this shift from CPU only to specialized AI computing changes exactly what you can achieve sitting at your desk. So the days of looking at a computer box and only checking the CPU clock speed, those are officially over. The future of PC buying requires a much more holistic view. Future devices are going to be judged by a much wider matrix.
It's the combination of CPU performance, GPU power, dedicated AI acceleration, the speed of that unified memory bandwidth, all balanced against battery life, deep software support, and localized security. The best computer of tomorrow isn't necessarily the one with the fastest single processor. It's the one where all these components communicate the most effectively. Which leaves us with this final, incredibly provocative question to consider. Will your next computer just be a local AI agent? If the heavy lifting of writing, coding, file searching, video editing, and daily automation is handled by localized, personalized AI models running directly on specialized hardware like the RTX Spark, is the traditional personal computer actually becoming an AI computer? It is a fascinating frontier, and understanding the core concepts we've mapped out today puts you right at the forefront of that revolution. Thank you so much for diving into the source material with me on this explainer, and I really hope this leaves you eager to explore the new era of computing on your own.